name is Lori Waugh, and I'm a graduate student from the Earth, Ocean, and Atmospheric Sciences Department at UBC, and I'm here to share some of the work that I did to investigate seasonal and spatial trends of dissolved copper concentrations and copper speciation within the Strait of Georgia. This project was in collaboration with Metro Vancouver's Georgia Strait Ambient Monitoring Program. So to begin, while copper is a metabolically essential micronutrient to marine biota, copper can also become toxic at relatively low concentrations, which becomes especially important for coastal environments such as the Strait of Georgia. This toxicity depends not on total dissolved copper concentrations, but rather the concentration of the most bioavailable species, free hydrated copper 2+. However, to determine the concentration of copper 2+, you need to account for the 99% of dissolved copper that is chelates by a pool of organic ligands within the marine environment that then decrease the concentration of copper 2+, thereby buffering copper toxicity. This pool of ligands that you find in the environment are a diverse mixture that can include terrestrially derived humic substances, biological macromolecules from municipal wastewater, and ligands produced by phytoplankton and bacteria. In the Strait of Georgia, we wanted to measure the dissolved copper concentrations and organic copper ligands in the strait to understand the seasonal and spatial variability within the Salish Sea, as well as determine the concentration of and extent of toxicity due to copper 2+. To do this, we sampled between 2017 and 2018 in 4 stations, 1 at the northern Strait of Georgia, 2 at the southern Strait of Georgia, 3 at Harrow Strait, and then 4 at Juan-de-Fuca Strait. And we monitored the seasonal variability of copper speciation in the strait by collecting samples at our Southern Strait Station 2 for the months of September, December, April, and June. In order to determine ligand concentrations, we titrated our samples with copper additions in the presence of an added ligand of known binding capacity for copper, measuring the change in signal proportional to the concentration of the copper bound to our added ligand. This data is then fitted with a program called ProMCC, which balances equilibrium equations between the different species of copper in our sample in order to output ligand concentrations into different clusters of the sample's ambient heterogeneous ligand pool. These clusters are typically described as L1 type ligands and L2 type ligands, where L1 represents the strongest copper ligands detected within the ligand pool with a conditional stability constant greater than 10 to the power of 13. And then the L2 represents the weaker copper ligands detected within the ligand pool with a conditional stability constant less than 10 to the power of 13. So by knowing the concentrations and binding capacity of the ligand classes in the sample's ambient ligand pool, we can then determine the concentration of the bioavailable copper species, copper 2+, as P copper. And then here's our spatial data set. Immediately, you start to see that dissolved copper concentrations in gray on this plot and the copper ligand parameters in blue vary between stations and depths to a similar pattern to that of salinity in black. And the weakest ligands were found in the southern SoG surface waters nearest the Fraser River, and the strongest ligands found in the deep waters of Juan-de-Fuca Strait, which is filled with incoming Northeast Pacific waters. This is consistent with what you should expect in an estuary environment where weaker ligands are typically terrestrially derived and are inputted into the environment at high concentration from rivers, and then where the strongest ligands typically are produced in low concentrations by marine biota and are typically the dominant ligand class within the ligand pools found in the open ocean. And for dissolved copper in Juan-de-Fuca Strait, dissolved copper was maximum in surface waters, but converged to the same concentration as was found in coastal Northeast Pacific water, which was collected in August 2012 and is shown with a dotted line on my figures. And then here's our seasonal data set. Again, you can see that dissolved copper concentrations and the copper ligand parameters vary between seasons and depths to a similar pattern to that of salinity. Within the top 50 meters of the second station in the southern Strait of Georgia, dissolved copper and dissolved copper complexation parameters are strongly influenced by the seasonal near freshwater discharge of the nearby Fraser River. The maximum dissolved copper concentration of all seasonal data is at the very surface in June, which is where the Fraser River freshet is at its maximum. As well, the greatest copper speciation variations between seasons in all of the seasonal data were at the shallowest depths, where 2 distinct ligand classes were often detected. And within these surface depths, the stronger ligand, L1, concentrations range between 10.5 to 15.7 nanomolar, with a log K value between 13.5 and 14.3. The weaker binding L2 concentrations range between 30.9 to 107.7 nanomolar, with log K values between 11.5 and 12.3. In particular, differences in L2 follow trends in salinity, where L2 is maximum in June surface waters. This indicates a large input of weaker L2 ligands from a terrestrial source. And then we've since taken this data set and explored comparisons between ligand parameters and complementary data from our samples. And I've also clustered this data set to explore trends and the potential for modeling the copper binding ligand pool within the state of Georgia. And we're preparing a paper to submit soon. So if you're interested in learning more about this, feel free to contact me and I can share that with you when the time comes. But otherwise, thank you so much for listening.